for jumping in, folks. Okay, it is 8:02, at least my time, but I know we're in a lot of different time zones here. So let's go ahead and get ourselves started. Oh, good. We've got some folks coming in from Germany. Really do have a global view here. So thank you, everyone, for joining and welcome. My name is Karin Landers. I'm the Staff Product Marketing Manager here at Ververica. And today we're going to be calling out an industry-wide problem that's costing our organizations potentially millions. Joining me today are Jaime López, the Director of Product Excellence here at Ververica, and Giannis Polyzos, who's our Principal Streaming Architect. Now, Ververica created open source Apache Flink and defined the standard for stream processing, and today we're here to show you why dual pipelines are done and what's replacing them. So let's get started. So our agenda for the day, we're going to start by talking about Ververica Streamhouse, what it is, what it introduces, and why a decade of stream processing experience has led us to this point. Then we're going to get into the problem itself, namely Lambda Architecture. We're going to use the financial services industry as an example throughout our time together, otherwise known as FSI. And we'll talk about how escalation happens, what the freshness spectrum actually means for the business, and why divergence isn't a data quality issue, it's actually a compliance event. From there, we'll address the conceptual shift. How can we stop reasoning about engines and schedulers and start reasoning by freshness and intent instead? That sets up our solution, Materialized tables. One SQL statement, schema extracted automatically, scheduling completely handled, resources isolated, and the execution mode is not your problem anymore. We'll also address cost, because Lambda doesn't cost just twice. It actually costs in a compounding way. You end up with compute, engineering, reconciliation. Each one is completely unbounded in its own direction. Of course, we'll have time for questions at the end. Anytime during this presentation, please feel free to drop your questions in the Q&A chat section down at the bottom of your Zoom. And if you want to go any deeper after the session, we're all happy to jump on with architecture reviews or to dig in a little bit more one-on-one as well on calls afterwards. So 5 parts, 1 argument. Let's go ahead and get into it. So dual pipelines are an architectural snowball of sorts, and Ververica's Streamhouse represents a decade of stream processing expertise that stops that runaway effect. Streamhouse is the architecture built in Ververica's platform, and it helps solve a major issue. Decades ago, the data industry got stuck in a data processing architecture binary. You can have fast or you can have cheap. You can have real-time or you can have batch. You can have streaming or you can have lakehouse. But that trade-off wasn't actually meant to be a forever problem, especially when it's entirely an architectural problem. So we know that traditional lakehouses are cost efficient. They're also slow. By the time the data lands, the moment to be able to act with that data has potentially passed. Fraud's already scored, your positioning has been missed, your opportunity is gone. So decisions are no longer in your control at the time that they would potentially make the most impact. On the other hand, we also know that real-time streaming is quite fast. It can also be quite expensive. You end up with always-on compute, peak provisioning, payment at the same rate when you're on at a Sunday at 3 a.m. that you would expect during a Monday at regular business hours. But Ververica Streamhouse closes that gap. This isn't a compromise, it's a complete unification. It's lakehouse native architecture, so every freshness tier is covered. It's sub-second streaming to daily batch. It's one platform, it's one set of semantics, it's one source of truth. So you declare what data you need and how fresh you need that to be, and Ververica platform handles everything else. That's the Streamhouse, and that's what Ververica's built. Let's make this a little more concrete. Every layer in Ververica Streamhouse has a job. Let's start at the foundation, autopilot. This is your auto-scaling service. It's continually monitoring resource utilization, and it scales in real time. It also supports scheduled scaling for known traffic peaks. So your system right-sizes itself. You're not having to sit in there babysitting it. Above that, storage, 2 tiers. We have Flues for our streaming storage, which is real-time key value plus log. This is columnar, it's lakehouse native. Below that, open table formats are aligning with the lakehouse storage. This is our object storage, and critically, tiering between the two is automatic. It's union reads across both layers, so there's hot data where you need it to be and cold data where it belongs. And Giannis is going to dive into this a lot more in a little bit as well. Then there's our processing engine, Vera. Now, Vera is Ververica's proprietary, incredibly powerful engine that unifies batch and stream processing. It's one engine, one runtime, and there's no context switching between those paradigms. At the top, materialized tables. This is the application layer. Declarative SQL, freshness-driven refresh. This is unified query interface, so you're writing the intent, and then Ververica platform is executing it. Over on the right, workflow scheduler. This is our batch execution, triggered on a freshness threshold or on a schedule, so bounded refreshes are planned and registered automatically. Every layer running in Ververica's Streamhouse architecture within Ververica's platform feeds the next layer. Nothing ends up being duplicated, nothing ends up being reconciled. This is what unified actually looks like. So what are we announcing today? There's a lot of features that are an exciting part of a release, but fundamentally they're adding up to one bigger vision. Dual pipelines are done. It's not dual pipelines are hard or dual pipelines are expensive. They're retired. We don't need them anymore. So let's talk about what that means in practice and what's making that actually possible. So materialized tables, again, we're defining our data product once in SQL. The platform maintains it over time. There's no separate pipelines, no duplicate logic, and most importantly, there's no drift between what your real-time system is saying and what your batch system says. Also, our freshness-driven execution. You don't need to choose the engine. You simply declare how current the data needs to be. The platform looks at that freshness requirement and then selects continuous streaming, incremental batch, or scheduled batch automatically. That decision is now operational, not architectural. Our built-in workflow scheduling. Bounded refreshes are planned and registered automatically within the scheduler. You declare intent, orchestration follows. Resource queue management. Always-on streaming workloads are protected from batch interference. This is important to have this hard isolation between workloads of different criticality and different freshness tiers. Your fraud detection job does not need to be competing with your settlement report for the same compute resources. This is not just a simple feature release. This is a completely different way to build a data infrastructure. One powerful platform, one runtime, one ultimate truth. So at this point, I'm going to go ahead and hand it over to Jaime to explore all of this a bit more.
Thank you very much, Karin, for setting the scene for us today. My name is Jaime, and I'm going to first give you a quick note on scope before we dig in. This whole talk is framed around financial services. The reason for that is that it's a vertical where we see this issue of dual pipelines very often with massive impact. However, the pattern is universal. We are solving the most complex use case, but this is translatable to many other verticals, from IoT to energy to retail. The focus today will be on FSI though. There are 4 core reasons why this is a problem in FSI. The first one is that freshness diversity in FSI is wider than almost any other industry. What I mean with freshness diversity is that you have use cases like card authorization, which is sub 100 millisecond. Then on the other end of the spectrum, you have annual regulatory submissions from the same underlying transaction. Almost nowhere else you see that range from 100 milliseconds to a year. The second reason is that the consequences of inconsistencies are probably the most severe. If you have diverging numbers in a risk report, that's not just a data quality ticket. It's probably a compliance event with the regulator. And the regulator will ask which of these numbers is incorrect. You might incur a fine. Number 3 is that the market conditions in FSI demand freshness agility. Rate decisions, flash crashes, end of quarter, short squeezes. These often mandate real-time requirements that kind of appear and disappear without warning. You have to be always ready. And number 4 is the regulatory framework. Regulatory obligations make this dual pipeline-induced debt structurally quite dangerous. You have things like PSD2 frameworks that treat the Lambda architecture we all know and love as a liability, even if they don't name it. But this pattern, as I said, is everywhere. E-commerce with Black Friday or Singles Day, logistics, telcos with network anomalies, gaming with live fraud, healthcare, patient monitoring. It's the same pattern. The stakes are just different, but the solution is going to be the same. And to elaborate on the freshness spectrum, FSI institutions operate data products across that full freshness spectrum that I mentioned, from 100 milliseconds to yearly from the same transaction data. This is the industry reality that we have to adjust our architectural decisions to. And now that we're talking about architecture, each of these freshness tiers currently demands a different architecture, different engine, maybe different store, different code base. We are pretty confident we have a solution that changes the game there. And that allows us to avoid some of the nefarious consequences here, which are when you have two systems with the same metrics but no guarantee that the numbers will agree, you are potentially incurring very serious risks. And again, we are confident that doing away with dual pipelines will shield you from these consequences. And it all starts with good intentions. We often see that a Lambda architecture starts with a batch job that works. That transactions come in, Spark process those maybe daily. You land the results in Iceberg. Your regulatory dashboard shows like the day after data. That's perfectly fine for these T+1 requirements for relatively slow. At this point, the problem hasn't started yet, but the conditions for the storm are set. Because now you have a production pipeline whose latency is permanently lower bounded by Spark's batch model. What I mean is that you can never get a latency below the Spark batch bound. And business requirements will eventually demand something faster. But we're at stage one. Everything is fine at stage one. Sun is shining. Let's see what happens next. And then, a little bit later, next quarter, next year, fraud operations comes back and says like, hey, we cannot really do our job with daily data. We might need hourly data. Seems like completely reasonable ask. You tighten the cron job, you ship it, works, stage two, fine. But then probably market risk or exposure control comes back to you and says like, hey, we actually need a 15-minute assessment of the value at risk when our trading desk is operating. Because during these volatile trading sessions, we just had quite many last week with the Hormuz Strait crisis. These hour-old positions create real risk for the desk. You might have a lot more value unhedged out there in exposure than it's acceptable for your desk at a time when commodities fluctuate very much. Again, this is a very reasonable requirement. Maybe you try to run this same Spark job every 15 minutes and you'll start hitting some problems. Maybe your jobs overlap, your resources get tied. You can maybe make it work with enough engineering sweat. You're strained, but functional. But then let's say something that we also see often, anti-money laundering or compliance, comes and says like, hey, now we have actually a hard requirement from a central bank or from like OVIC from the US to have sub 2-second alert latency from money laundering suspicions. These have to fire before a transaction settles. And however we want to look at it, there is no batch answer to this. So let's say that, okay, we go state of the art, you build a Flink job, you add kind of Kafka to move the data. Now you have a streaming layer. You have added a second pipeline. And here's the thing I want you to hold on to. Nobody really here made a bad decision at any point in the sequence. Every individual request, every individual requirement was reasonable. Every engineering response was the right choice given the constraints at that time. You didn't design for this Lambda, but it was kind of built by accumulation, one good decision at a time. But then suddenly you wake up and you have two separate pipelines producing kind of the same metric from the same data and no mechanism to reconcile them. And I'm going to stop here because understanding this is important because it means that the fix isn't better engineering. The fix is a different architecture. And what I mean with the fix isn't better engineering is that all of these things are defined by the business. All of these requirements have an inherent freshness SLA with real consequences if we miss it. If we approve in the realm of fraud operations, we approve a card transaction before we check thoroughly that this is not fraud. you're going to have direct fraud loss with no good fix. Transaction is gone. In AML, if you miss the like a suspicious pattern or an alert, you're going to be in compliance breach. We just saw a number of banks in Europe get fined hundreds of millions of euros for subpar AML practices. In market risk management, if you have volatile sessions and your value at risk is not tightly controlled, again, your desk can go bust. This is the kind of mistake that if happens, you don't hear it in a meeting, you hear about it in the news next day. And maybe some of the more severe but less timely capital ratios or treasury. These have to be accurate for end-of-day regulatory submissions. We have customers that face very heavy penalties if they breach this, and hence they kind of invest a lot of effort in the end-of-day treasury report to the central bank. These are not the same problem at different speeds. They're four unique different problems, four different SLAs that all are generated from the same transaction. That's where the architectural divergence comes from. It's not about design. It's four real, legitimate, non-negotiable requirements that sit at different points of the freshness spectrum, from the extreme left to the extreme right. And this is the root cause, that one transaction, that somebody making like one bank transfer or one large card purchase requires 6 downstream consumers. Maybe the fraud scoring, less than 100 milliseconds, AML monitoring, less than a minute or two, position keeping, maybe 5 minutes, intraday value at risk, 15-ish, credit exposure, maybe half to 1 hour, and settlement, reconciliation, end of day. 6 orders of magnitudes of freshness for the same underlying transaction. Today, often that means 4 to 6 separate pipeline architectures that consume from the same source. And this is what the business has required so far. The question is whether you're going to meet these requirements with 6 architectures or with 1. And more importantly, can you even guarantee to agree on the answer if you have 6 architectures when they're all reporting on the same underlying data? We'll see later, Giannis will show us that is not a guarantee. That's why sometimes we see that we end up in a Lambda architecture where the batch layer produces this T+1 regulatory metrics, the streaming layer produces the kind of short latency one, real-time operational metrics, both called the same metric with the same name. But the question I want you to ask yourself is like, what will you do when the top and the bottom don't agree? When they report a different value for the same metric over the same time period, which one is correct? And the tricky part here is that there is no answer. There's not kind of, we need to investigate. No, structurally, there is no answer in a Lambda architecture. The two systems have been implemented separately, they're maintained separately, they have developed different semantics over time, they probably have different windowing boundaries. They probably handle late arriving data in a different way, probably have different business logic. And they even end up in 2 separate code bases. So this divergence is not a bug. It's a structural property of Lambda. And I want to make this precise before I move on, because this, like the easy answer seems like we should reconcile our batch and streaming better. We think it misses the diagnosis. You can't really reconcile your way out of a structural property. How does this look in practice? It ends up being 2 systems, same metric, same time period, but 2 different values. For example, here in one of the simulations we run, you end up with your batch side of Lambda reports 2.47 million and streaming 2.61 million, and you have a delta of over 140,000. Somebody has to put a number in the regulatory report. Which one you put? And how confident you are. In a Lambda architecture, that is genuinely hard. You're going to have to trace through 2 separate code bases, 2 separate storage layers, looking for the specific semantic difference that caused this delta. Maybe it was that late arriving event that was handled differently. Maybe it was like an edge case on your windowing. Maybe it was a logic change you made to one of the pipelines 6 months ago, but you never propagated to the other. And then you find it, fine, you patch it, you kind of decide for yourself what's the truth. But next quarter, you're going to have the same. And the other quarter, the next month, you're going to have the same thing because you actually haven't fixed the condition that created it. You fixed this specific, let's say, symptom, but you haven't fixed the root cause. There's another potential response to this, which is like, okay, go Kappa architecture. Have a single streaming pipeline, no batch whatsoever, no diverges by design. And Kappa, we think, is kind of correct on the consistency argument. You know, you have one single computation graph, one result, not disputing that. But we think that Kappa solves the wrong version of the problem. Because of the reason that Lambda exists is not that the teams prefer two pipelines. Lambda exists because streaming pipelines couldn't be trusted to produce accurate results at the time that they were built. And the batch arm wasn't redundant. It was kind of the correctness guarantee. But Kappa, without accurate streaming results, just moves the risks from divergence to single pipeline inaccuracy. Instead of having two things that disagree with each other, you will have one single answer, but you still cannot trust that it's the right one. And structurally, it also creates its own set of problems. You're going to have issues with provisioning 24/7 at peak allocation, regardless of the volume. That's pretty expensive. It's going to be tricky to do streaming replay when you have to backfill for regulatory reports. And now you have a single failure mode, a single, let's say, critical path that impacts all the freshness tiers simultaneously. So what we actually need is accurate streaming results plus the ability to serve different freshness tiers at a reasonable cost. That is the gap. And that's why you're going to hear many times today us talk about materialized tables. What they do is not simplify a two-pipeline architecture, but they basically retire the condition that made the second pipeline necessary in the first place. You're not simplifying Lambda, you're banishing the workaround forever. And yes, like we have gone back and forth with this. There are trade-offs. You can always do everything, sure. But do you want to deal with the complexity of two code bases? Is that the best usage of your engineering time and effort? Double storage, two operational runbooks, having to propagate changes of logic semantics in two code bases. Do you want to deal with the cost of two clusters at peak provisioning all the time? Every weekend, every bank holiday when you have fewer transactions, regardless of volume, do you want to maintain this? And do you want to deal with the engineering effort and, let's say, burn of having to maintain every metric, every incident, every schema change twice? And you know that this will compound as your catalog grows. So we do think that there's a better way of solving this problem. And that problem means that we do away with dual pipelines and we settle on one single solution. And now I'll hand over to my colleague Giannis, who's going to walk us through the conceptual shift.
Hello, guys, and thank you. So bear with me for a moment where I'm trying to do my best to screen share. Can you see my screen?
Yes.
Thank you,
Yes,
guys.
we can.
So thank you, Jaime and Karin, for setting the stage. And actually, Jaime did a really great job at highlighting the problem. And the question here for us and all the work we are doing, because we have been operating in the stream processing space for years, is all these are patterns and common things that we have been seeing throughout the industry for years, and things that almost every actually customer and overall people we're working with is facing the same challenges. So instead of trying to, create a solution on infrastructure we know it doesn't work, the question is how we can take all these limitations and basically work past them for, let's say, the next day of streaming systems. So, as Jaime again highlighted, enterprises end up with two data pipelines, and it's something not even a gap architecture can solve, right? Because if you're adopting and operating as a team only on streaming data, then it might make sense. But again, there are some limitations. However, also org-wise, this is not feasible because batch pipelines are the norm and indeed much needed. So our response there was to rethink the wider architecture and and this is why we also invest into new technologies. And as Karen presenting in the beginning, the Streamhouse is our response to that. Our focus in this webinar, specifically and what we'll see next, is the high-level abstraction of the materialized tables and actually understand what it means to actually create a unified streaming data platform and overall platform that not only that only batch and streaming not only coexist, but they are also available and easy to use from non-streaming engineers, because this is also an important audience that doesn't get enough attention. So for us, what if we started from a different question than the one we have been asking and focus on reasoning on freshness and intent? And think about the last time someone on your team built a new data product, right? What were the questions they actually spent time on? Like which engine, Spark or Flink, which storage system, how do I configure the scheduler, what is the right cluster size, how do I isolate this workload, how do I reconcile the batch output with the streaming output if I need it. And if you think about it, none of these questions have anything to do with the business logic of the metrics, right? They're all infrastructure questions. And these are great questions. However, these are engineering questions. And in the average data team that you're probably working with, the infrastructure questions take significantly more engineering time than the business logic questions. And the business team are a big part of the analysis and decision making. So if we ask, what is an actual specification of a data product? The answer to this will be, what data does it contain and how fresh does it need to be? Two questions, and these are both business questions. Everything else, the engine, the storage, the scheduler, the isolation, should be derived from those answers by the platform. And this is what we're trying to build. If that platform isn't doing that derivation, it's outsourcing basically infrastructure decisions to engineers who should be working on something else. And this is what derived from intent looks like in practice. The query on the left is the business logic. Standard SQL, it doesn't change based on the execution mode. It's the complete specification of what the metrics it contains. Same for streaming, same for batch. Now the freshness value on the right is the actual SLA. It can be 30 seconds for fraud, 15 minutes for value risk, 1 hour for credit exposure, 1 day of regulatory. The business actually says those SLAs. It's the same query, different freshness, completely different execution strategy. And most importantly, the business logic is identical. There is no such thing as streaming specific SQL or batch specific SQL. There is one SQL statement. And the practical thing here is that when fraud operators change, for example, their freshness requirement, let's say at first they had 1 minute, and then they want to lower it to 30 seconds. All you have to do is issue one button click. You don't touch any code, there is no pipeline to build, there is no divergence risk from having two implementations of the same logic. And this is the complete unit of data product. And basically it is the table, right? Not the job, not the pipeline, it's the table itself. Four properties: the name, the schema, the query, and the freshness. The schema is derived from the query, you don't write EDLs. The query is the business logic written once. Freshness is the SLA expressed as a time interval. And then from those four properties, the platform derives the execution mode, which can be a streaming mode, an incremental mode, and a batch mode, the scheduler configuration, the resource alignment, the lineage, all of it automatically. And the important here is that, again, with the altering the freshness, when you just alter, the platform rederives all of that downstream. You manage intent and just that. The platform manages infrastructure, and if the platform isn't doing that, something is wrong probably with the abstraction. So again, our solution to that is the materialized tables. And this is what the materialized table actually looks like in practice. You run your create materialized table statement, you specify the freshness and the business logic, nothing more. This is a complete data product specification, and it's simple enough for your less technical folks that are not those amazing streaming engineers to actually use in production. And then with one knob tuning, you just also based on the SLA changes, you can update that freshness. Like we have, when you write a query and you specify the freshness, you can run a continuous streaming query, which can be, for example, seconds. If it is typically to the minute level up until 3 minutes, then the edging translates that as incremental processing, and during each interval, it just keeps track of the incremental changes and apply those. And then you also have the schedule batch, which is a batch job that gets scheduled on a workflow scheduler. And we'll see in a bit how these things look in practice. And this is basically the target architecture, and this might be similar with the medallion architecture you're familiar with. Like you have your data lake, your data lake house, and you have this logical layering with bronze, silver, and gold tables. But here, the difference is that the pattern that they call data continuity, and basically means that if you want, you can apply streaming and everything gets upgraded, gets updated automatically, continuously. But because, again, different business requirements have different SLAs, you also deal with freshness. And this is something we are taking into account. Schema extraction is also worth a specific note because it closes a class of operational problems that's unappreciated. That you might have seen lots of buzz around the data quality these days. In Lambda, you maintain schema definition in multiple places: the path table schema, the streaming store schema. Every column addition propagates twice. Every type change propagates twice. And the schema drift between the two layers is one of the most common causes of metric divergence we see in actual production systems. It's not the bugs, it's not the logic errors, just the schemas that drift because a change was made to one pipeline and not the other. Materialized tables derive the schema from the query. The agents analyzes the select clause, infers the column and the types, generates the DDL, registers on the catalog. You don't have to write anything. One source of truth, zero schema drift, because there is only one layer. Now, there is also the cost argument, right? And of course, for many things, there is also some learning curve. But after that, like we have the Lambda architecture that basically has three cost categories. The first two appear in infrastructure invoices. The third doesn't, and it's often also the most expensive one. Like you have the compute one, which basically you have two clusters, both at peak provisioning, both 24/7 running. Imagine that at 3 a.m. on a Sunday, and we'll see this in the next slide with an example. When transaction volume is minimal, you are paying for full capacity. The stream allocation doesn't scale with demand, it scales with your worst case SLA. Then there's the engineering part. Every metric has two implementations. Every schema change propagates twice. Every incident that has two independent failure modes to investigate. New engineers need to understand two paradigms and two operational runbooks. And this compounds as your metric catalog grows. And finally, we have reconciliation, and this is the unbounded one. When numbers diverge, someone investigates, explains it to the business, patches both pipelines, documents the root cause for audit, and verifies the fix. That work has no ceiling. If the divergence surfaces in a regulatory submission, for example, the cost extends well beyond the engineering time. And basically, I guess the specific claim I'm trying to make here is that the reconciliation cost is not just unquantified, it's unquantifiable in advance. You don't know how often the number will be wrong, how long the investigation will take, or what the downstream consequence will be. And this is that's what makes it structurally dangerous and not just expensive. And this is the example I wanted to make, right? It's Sunday, 3 a.m., and you see the peak here. And if your job is running 24/7, you're just wasting compute. And in Ververica specifically, we also have our autopilot which manages the infrastructure and can lower the resources, but it's still a streaming job 24/7. What also the materialized table allows you to do is that you can also tune the freshness, Maybe, for example, in those periods, you can increase the freshness and leverage the incremental mode. So the job starts at intervals, gets incremental changes, applies those, and then goes silently again. And then go back to the normal low latency spectrum when you have that actual peak. But again, this is a business decision. And this is basically the before and after between the Lambda architecture and the Streamhouse materialized table, so you can also visualize the differences. And basically now, the next part, let's go and see in action how these things actually apply. So, enough talking, show me the demo, show me the code. Now, what we have here is the Ververica UI. And this is how it looks like. And what I can do is I can go to the catalogs here. And what I want to show you is basically from here, the catalogs allow you to create to multiple external systems and just get direct access like here, for example. You can see the different tables and get direct access to everything on the external system. And here in this table, we can also see the lineage. And this is basically something like a medallion architecture in practice, right? This is what the data lineage looks like, and basically what we have is our source tables, and up until here we can consider is the bronze layer and the ingestion. Then if we go up to this point, you can consider is the silver layer where we have our enriched data. And finally, we have our gold layer and the business aggregates. Let me zoom in here. So basically, what I have here, let me fix it. So what I have here is a 360 view, and basically I have my source tables that basically create this 360 view, and this 360 view is not updated on batch, it's updated continuously by streaming, which means with every new change it updates. And then I have here my transactions table, and for every incoming transaction I can enrich it from the 360 view, and from there I have my erase transactions. And from there, I apply aggregations and I have my aggregations tables and KPIs ready to be served. So then the SQL editor, I can go, for example, here. Let me find the query and let me query this third 360 view table. And I can run this on my session cluster, wait for the data, and basically here from the templates we can see the users have the option to run streaming drafts or batch drafts, which equals to streaming or batch jobs. And in this case now I can also go here and from the editor also visualize my data. And since this is a batch query, the data is static, but for example, if it was, if I had selected and run a streaming query, I could see here on my editor everything running continuously. But again, this here means that we need to create streaming or batch tables, which some users might have to deal with watermarks or other things. So next, let's see now how we can do the things differently. So if I go back here to the catalog and I go again to the data lineage, remember, this is a continuously updating pipeline, like everything is streaming. But again, as we saw, different jobs have different SLAs, and it can be seconds, minutes, or hours. So let's see basically now, after all this, how we can do better with the materialized tables. So if I go here on the catalogs, let's go to the catalog. I can create materialized table here, and this is the editor. So let me copy and paste the materialized table here. So this is my materialized table. I can click debug here and actually verify again my session cluster that my query works and I can actually see data. It also has built-in intelligence, so if you have any SQL errors, it will the ID will tell you that, and here are the results. So as you can see, I have my query and I have just the freshness here, and the rest is the business logic, nothing else. So the freshness here is 5 minutes, which means it's going to be an incremental job. And the engine is clever enough to derive it. So let's go and create this thing. And right now my materialized table is being created. And right enough, everything is there. And you can see properties, some basic information here on the freshness has been extracted. All my properties are there. All the schema table is derived from the SQL clause, and you can see here everything. And finally, I also have my business query here. So with that, let's go and click start here and run it on my queue, and we'll talk about queues in a bit because they're also important. So let's wait for this job to start. And while we are waiting, let's also go ahead and also create a second materialized table, which we will base it on the first one that we just created, which is a business summary for 2 hours. And this should be a batch job. And we'll see how the engine is clever enough to derive that. Let's wait for it to initialize. You see again the same story here. Everything has been generated. And I can also run this on my default queue. So now that we have all this, let's see. Let's go here again. This should have started now, and it's in updating state. So if I click here, it will get me to the deployment of this, and I can also set the status here, and I can see my job is up and running. So now, yeah, the other thing is here is the freshness is 5 minutes, right? So as I said, with just one button click, we can modify the freshness here. For example, I can set it to 1 minute, seconds, or even hours. And the engine will be able to derive that and adjust accordingly. There is nothing else. There is no new pipeline, nothing I need to do. So with that now, the other thing is this batch job. You can see it created here, and it's also updating. So this means this has started. So now what happens here? If I go to my workflow scheduler, I can see that the job is here. It has been automatically scheduled for deployment on the workflow scheduler. Didn't have to do anything. No, not create any DAGs, no anything. And to show you this better, if I go to this 3060 DAG, I can see here, you can also see how it ran and the diagrams here show the complete DAG and how everything has run, different metrics like the duration and other job details. And if I go here, I can also see more, the deployment. And the other part here is that if I go to the diagrams, I can see again here, I can go and I can add tasks and I can add more dependencies in this tag and extend it. And this is basically how you're creating everything, also manually, if you want to use for other use cases. Now, the thing here is that after all this, we run into another issue. Now we run batch and streaming jobs. So the question is how we avoid resource contention. And our response to that is resource queues. So I have one queue here for batch jobs, the workflow, and I have another queue for my streaming jobs. So this means that when a batch job tries to go up, it won't compete with the resources, and we find resources available to actually run. Otherwise, there is a high chance to run into resource contention issues. And yeah, I think what else do we have? The final part, let's also go here on the materialized tables. We have the data information, which will basically give us some information for the tools. We have data preview, and I can go here and run things on my session cluster to also get some data and see some sample output. Right? Let's wait for it. And finally, we also have the data lineage, and you can see how different tables are here and linked together. So I think this was all for the demo, and now we can go on Q&A. And Karin, I think I'm going to give you back the sharing.
Great. I think there's one that came in the general chat, and then we'll take a look at the questions also, which I think, George, thank you for a reply to that too. But perhaps Giannis and Jaime have some more to add to that also while I
Mhm.
take back over sharing.
Yeah, brilliant. So let's start with the questions. I thought that there were a few really good ones here in the chat. And I know the answer to this one, but I think that either Karin or Janice are going to answer it much better than I am. Which is by Babatunde Oyo asking, what if the business logic cannot be properly represented by a SQL statement?
And I think I think also George answered it below that
There
because
you go. Yeah.
there are the UDFs, the unified functions in Flink, so you can just leverage that and express the other things. But again, the platform and Flick itself has a variety of APIs. So for you, you have all the tools at your disposal to basically choose the right abstraction for the right job. You have the Python APIs and DataStream API, you have the Java client, you can use normal SQL, or you can use the materialized table. The important thing here is that different teams in one platform can choose how they want to create and deploy their jobs. So basically, flexibility, let's say, is the keyword here.
Yeah, to add on to that, I think we've been talking for the past 48 minutes about one pipeline. And in my opinion, that's the big power of this, that whatever your requirement is, like if it's SQL flow because you have data engineers involved, or if you need something more complex with windowing and like you can use UDFs or you can use Java, you're going to be able to keep the one pipeline, the one kind of logic and architecture.
And kind of as a final on that, we've been talking quite a bit between Ververica and open source Flink also. Keep in mind the platform is 100% compatible to that. So this applies to both of those bits as well. And George, thank you for your addition in there too.
But there is also another question, is the materialized table backed by only one data source? So basically, when using the materialized table, in order to get data in, you can use the CDC pipeline and basically everything that the Flink CDC project supports, which is a variety of sources from operational database like Postgres and MySQL to Kafka, for example. Now, the materialized table itself as a storage runs with two different systems, and this is what we saw on Ververica Streamhouse. Basically, you can either use it actually right now. Only Pymon is supported because Pymon is a streaming data format that it's the only one capable of supporting both streaming, incremental modes, and batch modes. However, there is also Iceberg compatibility, which means you can use it to actually query the data. And soon, uh, we're also going to port support to run it directly with our low latency streaming storage, Apache Flux. So basically, you have a variety of data sources, but the storage itself, it needs storage that is actually built for streaming to be able to support all three modes. This is why we also invested in the storage a lot.
Yeah, I think that covered also something that people asked before, or we got a couple of questions by email before the webinar, like what are the future plans? What does this mean storage-wise? I think that kind of covers it, that yes, streaming storage is needed, but we have already a wide array of storage formats covered, and there are more and more relevant ones coming. Now at this time, I want to also encourage people, if you have any further questions, do write them either in the chat or in the Q&A. We will answer them. And in the meantime, I have another couple of questions that were sent by email before.
Mhm.
Um, and one of them is actually pretty detailed. It's like, okay, what happens when a freshness interval changes at runtime? Does the job restart or like how does this work?
Yeah, so basically, this is what we saw in the demo, right? Because when you change the freshness, like for example, assume I have my job that is running at seconds or minutes. Now, if I change this freshness and make it, for example, 1 hour, it's just going to adapt the job and take it as a batch job and schedule it on the workflow scheduler, so there is no risk there. On the other hand, if it's a batch job, it's going to change the freshness. Let's say from 2 hours, I want to make it an incremental job that runs every 5 minutes. So it will try and do the best possible transition to make it to deploy it directly as a streaming job. The point here is that you don't have to rerun like different business logic, test a new job, deploy a new job in production, anything. You just modify everything with a button click.
Great. Thanks, Giannis, for the answer. Do you have any other questions? Anything from the audience?
I see one popping through on here. So from a cost perspective, what does unified batch and streaming actually mean, and why should someone consider it?
Oh, nice question. So basically, we saw some things around Lambda architecture, but there is a wider, let's say, discussion here. Because at this point, we also look at the materialized tables, right? Which is a high level abstraction, it's great. However, if you want, there is actually two parts, the platform part and getting a product, and the wider organizational thing with investing in the unified architecture. Now there, in the long term, there are we're working with a variety of customers in that, but this is more of a long run effort. But the way we are approaching and they are also approaching it is that in the beginning, there might be some, let's say, additional cost or effort because when you transition to these things, it might be some new technology you have to pick up. There might be some transition from the current architecture to the new architecture. But in the long run, as we saw, you end up, and this is something main companies also trying to do in the open source, like LinkedIn, Yelp, and other companies, you end up with a single tool set, actually a reduced amount of tools. You end up with single pipelines, you reduce your data copies, you deploy things fast because right now you only have one pipeline. So in the long run, the cost savings can be significant. But yeah, these things are also in their early days, and there are many companies that have shared their success story so far, but there's also a long way to go. But Yelp, for example, mentioned like 80% cost savings in storage. That's from reducing the storage cost duplication. So there's lots of it.
Yeah, I think
But
we touched some of it also with regards to specific use cases too. So there's the cost of the architecture itself or the infrastructure itself, but then there's also if you have something set to regulations, if you have something across audits, that kind of compounds on top of it. So
And
this was
actually, yeah, and actually for us, and this is the important thing to highlight here, like when we talk about cost, there are so many dimensions, and this is the important part. We need to take a zoom out and try to approach everything from the architectural perspective, right? Because if you just measure, like, okay, I have, as an example, my Kafka and my Flux, and get these things side by side, it might not be as, let's say, might be not the best approach to compare this because if one system can consolidate three more systems into one, then there is a huge benefit. So always take the overall architecture in mind when talking about costs. Yeah.
okay. Well, we're coming up on time, and I do have a little bit of conclusion on here. If you have additional questions that come up, we're going to be sending out the recording. Feel free to email back. We'll see that also, or contact us as well. So, yeah, let me just check one more time. Yep, looks like questions were cleared. Okay. Okay, so in conclusion, here's what we know right now. Dual pipelines are done. The cost, the risk, the complexity, none of that is something that you have to defend anymore. The future is unified. One platform, one runtime, one truth. Your real time, your historical analytics all maintained on the platform, not by individuals on your team. That takes time, effort as well. And governed absolute truth for AI that auditors can actually, or regulators can actually audit, and auditors can see the regulation too. So Ververica didn't just invent this future, we're actively building it. It's running in production currently at Tier 1 banks. That's why we've used those as examples throughout that are processing billions of transactions. global e-commerce platforms that serve millions of customers, our SaaS companies that can't afford to be stuck having to guess between their data metrics. So what we like to say, and you may have noticed some new branding that's been happening, check out our LinkedIn page also. While the world buffers, we act. And if you're ready to dive in a little bit further and stop managing dual pipelines and start building on a governed absolute truth, this first QR code here is the ability to contact us directly. Also, if you have additional questions, let us know. We'd be happy to set up time to show you how other customers are doing this today. The second code is the blog based on the unification of batch and streaming that we released also. And the third code is signing up for our free Apache Flink Bootcamp training course that we've been running. So as we've mentioned, Ververica are the original creators of Apache Flink. Platform is 100% compatible with it, and we run these boot camps that are done both asynchronously and live. And we've gotten a lot of great feedback on them as well. So I will also include these links in the chat right now, hopefully for everyone. Hopefully, and if it's not coming through, perhaps Elena can help me with that as well. But you'll be getting all of this information and resources likely by early next week from us. I'd like to say on behalf of myself, Jaime, Giannis, thank you so much for joining us today from wherever you are in the world today. And do let us know if you've got any questions that come up.
Thanks a lot, Karin. It's been an absolute pleasure. Thanks for hosting us. And thanks everybody for joining us today.
Thank you, everyone, for your time.
Thank you, everyone. Have a great day.
Bye, guys.